Oh, wow, it's dark. Oh, it's because of the screen. Let me see if I can just brighten it up. Yeah, okay. All right. I think we've got a few people here already. Well, by the way, I mean, last class, thank you guys for, driving on your own. It was pretty cool. I only got to see the last few minutes, but it was nevertheless fun to watch. Yeah, so today, let's see. We can just play it by ear again, right? We can play it by ear. We can talk more about recursion if you want. We can review some of the recursive functions you guys wrote last class. If that's something you'd like, we can review that and maybe try and write it in a different way, and also use that. Use what you guys wrote as a vehicle to segue into some of the nuances around recursion. What happens in the background, the man behind the curtain. So we can talk about that. What else? Yeah, and I think that will naturally introduce the idea of a stack, and then if we have time today, we can start implementing a stack in a different way, not like in Quest 8 where you have to use an array. So we can try to implement a stack today, or if we don't manage to do it today, we can continue on to Tuesday. We'll finish the stack next Tuesday. This is week 10. So is this week 10? This is week 10 or 9? I always keep hang on.
Week 9. Week 9.
Oh, it's week 9. Week 9. Okay.
Yep.
Right. So next week is week 10. So yeah, we do have a fair amount of time. So we can do stacks, implement stacks next week. Yeah. We review other topics, right? In the past, anything we've done so far that any of you, right? Not just the few people that are strong or have some experience, and who not the regulars who are just comfortable taking the screen and driving on, so who you guys are. So all right, so you guys are not allowed, but if any of the others, then you guys, right? So yeah, I mean, the last couple of lectures, the ones who are who've been regulars, they can basically just take off. You don't have to attend, unless you want to attend and help out. If people have questions or take over as typist or suggest things, you're welcome to attend. But I'd really like the lectures after we cover pointers and all, right? So I want any lectures left over. I want that to be for the benefit of the weaker students, right? First of all, I think it's very interesting. I think at the last department meeting, we were talking about students and how we can help some of the students who are struggling, and I think someone mentioned, yes, and this is one of the ways in which we can make the weaker students stronger, and it was really interesting. Maybe it's a culture shift, maybe, I don't know, because I think someone at least in the room, I think, was uncomfortable with the idea of calling anyone weak, and not me. I think the level of the comfort comes when you start attaching values to these things. I mean, if you say, it's weak, and I'm weak in several areas, but I want to get stronger in those areas, or I don't want to get stronger in it. It's my choice, really. But but it's important to recognize when you're weak, so you can polish up your skills in that area. Anyway, so how do we get talking about that? So I'd like the last couple of lectures at least to be for the benefit of the students who perceive themselves to be too weak to handle some of the more advanced topics in this class, right? Because once you get stronger, it's all as a piece of cake, as right? You talk to some of the other, so talk to the regular students, right? Because talk to some of the people who seem in your eyes to be very experienced, and strong. And if they have a good memory, right? I don't know, you got to also have a good memory, because many people tend to forget that they were weak once, right? So if they have a good memory, you talk to some of these stronger students, they'll tell you, right, at some point in their life, and they were also trying to learn, and they were equally mystified as you were, right, with some of these concepts. And it's just that it's been so long since then they've forgotten, right? And it's just that you discover, just because you went to Rome today doesn't mean that Rome only existed starting today, right? So, and people have been there before, but those people might have not have been to another city, may not have been to Shanghai, right? So it's that different people visit different things at different points in their life, and so it doesn't matter when you master a particular skill, but it's important that we know that there is a skill that, and do I want it or not, first of all, right? That's the most important decision, right? We have to make a decision as to say, well, at this point in my life, do I want C++ as a companion? Yeah, it's really, that's what you're asking. Because, if C++ is not going to help you, you don't want it, right? So how can C++ help you? Maybe it can give you a grade, and which lets you fulfill something on your transcript that lets you get into a college, okay, of your choice. Yeah, okay, so it has some utilitarian need, but I think in that case, if it serves your purpose that way, you may have basically got something out of C++, but you only got the tip of the iceberg. Right? It's not even the tip of the iceberg. It's probably a magic piece of candy that'll disappear once you actually look closely at it, really, because you think it's a reward, but really it's not a reward at all. You can live your entire life thinking, hey, I got an A+ in the CS2A course, and be very proud and feel special about it. But, as everybody knows, when we're close to death and we look at it and say, well, that 2A really improved my life or not, right? And so if you only use it as a transcript tool, right, so as a mark, a special distinguishing attribute that you have, then really it doesn't help you at all. At the end of your life, it's just going to be something you're going to throw away. It doesn't matter. You're going to say, did it help me, right? Do I want another chance to go back and relive my life without making all those mistakes, right? If I had another chance to rewind my life, would I still do CS2A, right? Because that's the question really you want to ask, right? Imagine that you've actually gone through your life, right? Just done everything, and then you've come back now to find out, okay, well, I've done it once, and when I died the last time, I was so damn sure that there were so many things that I did wrong, right? If I had a chance, I'll just go back and fix those things, right? So imagine that's already happened, right? Hypothetically, fictitiously, may not have happened, but I think it helps. I think it helps to imagine that it has happened in your life, and now you're back to say, okay, well, okay, so those things didn't really work out, right? And the last time I thought those things were really, really promising. I went down that path. I went down that path. I went down that path. So all of those things didn't work, right? So this time, okay, let me actually sit down before I go down those paths. Let me just sit down, play it out in my head, right? And imagine what's going to happen at the end. And then if you realize at that point that, okay, well, you know what? I actually needed to learn some skill really, really strongly, not because of the prestige it's going to confer upon me, but because there's something that I wanted to make, right? Something beautiful that I wanted to see and only existed in my imagination. And I wanted to. And in order to make that, I'm going to learn how to smith, right? Or carpentry, or chiseling stones, or programming, right? Anything, right? An art form, or acting, or whatever. So you learn that because now you found in your experience that lots of things really didn't work. All these things were just pieces of paper, right? Stock options, and then that these things don't work, and so you just want to show people that, yeah, here's some really cool stuff that you can do, which in fact you'll feel that when you're done with everything else, you'll feel that, okay, well, it hasn't been a waste. I've actually done something, so I don't have to come back to fix anything anymore. I go back and maybe I mess up something again, right? So I don't have to, right? So I think that's the reason why you should enroll in CS2A. That's what I mean, right? So in CS2A, unless you've really been absent, right? So let me put it this way, right? CS2A is a very hard course to fail, right? I mean, CS2B and 2C, I cannot say the same thing. Why is this being recorded? Hey,
It
it's
is.
automatically being. Okay, So today I actually deleted all the meetings that we had and then recreated this meeting. And then I noticed there was a checkbox that said, automatically record meetings. And then I realized, well, why the hell didn't I check it before? Because every time I keep forgetting, right? So anyway, thanks. Thanks for all that. Going with, anyway, I don't know what I was saying. But anyway, CS2A, that's a reason why you need to learn CS2A. And CS2A.
CS2A is
sure. You'll pass, right? You guys will pass, most of you.
CS2A has definitely helped me. The way that I look at like before CS2A, I did programming before. I was programming in JavaScript, which is kind of a higher level language. And there was a lot of things I didn't really understand, but I kind of took for granted, and I didn't really understand how they worked. But after CS2A, I understood how a lot of at least I'm beginning to understand how a lot of things in programming work. Like I remember, I think I don't know if that was the last quest or the quest before that, but with constructors and destructors and
which one are you on? Are you talking about quest 6 or
quest? I think either quest 6 or quest 7, and I think it brought up something about constructors and destructors, and how sorry, I'm blanking, but there were just a lot of sorry,
nuances like this,
yeah, a lot of things that there were, like for instance,
we take for granted in Python and JavaScript.
Like for instance, allocating memory and all that all those things you need to manually do in C++, that you don't need to do in something like JavaScript or a higher level language like that. So it was a very helpful class for me, and it also I think improved some of my coding practices as well, because there were certain things that I was doing before that now I realize I probably shouldn't be doing them, or I don't know,
no, I totally agree, Nathan. You know what, I think people have different opinions on this, but I believe that I come to the conclusion that C++ is in fact the first language that everybody should learn. But no, not strictly speaking like that, but they can play with JavaScript and other things, but they have to come to C++ before they actually learn real programming. And the reason I say that is because you take a messy, cluttery person, right? It's a messy, cluttersome person, right? And if they're in a small home, it's a small home, right? One room or something like that, and it's very messy and cluttery. And you can tell them, it doesn't have to be so messy and cluttery. But if they tell you, no, it's messy and cluttery because it's a small home, right? So it's a small home. That's why it's cluttery. If it's bigger, I'd have places to put these things. Look at these, drill stuff needs to go in the workshop, but everything is right here, right? So that's why it's all messy and cluttery. But what we tend to do, I think, is that no, it's possible to be neat and clean regardless of your space. And I think so that's the discipline. That's discipline, right? So a person who's messy in a small home is not going to be non-messy in a big home, right? It'll just be bigger mess in bigger home, right? So same thing I say when very long time ago when I was doing MapReduce and all these Hadoop and these things were there. I had lots of programmers who would say, there's simple tasks and they want to do it in the cloud and they want to do MapReduce and farm it out. But that's not the right idea. So in fact, that is a wrong idea. So something that is wrong on your desk is going to be wrong big time in the cloud. Right? So before you go into the cloud, you got to make sure the algorithm and everything is bulletproof and correct, right? Because you can't scale out to a trillion machines before you know that your one machine is not wasting cycles. And but at one point in history, I don't know, maybe you guys were really kids, right? So history, everybody was so crazy about MapReduce and Hadoop and everything, right? So and people were saying, oh, this magic bread, but it's been around for ages, right? It's just been given that name very recently, just like trees, right? right? Decision trees, right? This has been around for ages, right? Long ago, and it's only since machine learning picked up at MIT and Quinlan and all these people, right? So then decision trees become the rage, right? It's like that. So anyway, the reason I was saying this was because in C++, we get to learn discipline, right? It doesn't, and that's why C++ has so many rules, right? That's why C++ has so many rules, and it's important that we learn that discipline, because by learning the discipline of C++, we learn to be good housekeepers, right? So we know how to be lean and clean, lean and clean, right? Don't need anything more than we actually need, right? So we're not going to go and get stuff just because it's going to help us 10 years down the line, right? So we just keep a small house and neat house, right? That C++ trains you to do, which other languages don't, right? Other languages, and especially, I want to say, right? But there are other languages that have strengths, right? They are strengths, and there are languages that we need to go to for specific reasons, right? JavaScript, Java, Python, each of them have their own strengths. But I never understand people that say, well, that is the language for everything, or those are the only languages you learn. No, you have to go from something where you are the computer, right? So C++ is, strictly speaking, assembler or machine code, like John von Neumann, right? So that is the language you learn before you learn anything else, right? Because if you're bad in machine code, if you're bad in logic, right? Not even code, right? Thinking about logic, abstract logic. If you're bad in logic, you're going to be bad at everything, right? So assuming you're good in logic, assuming you're good in machine code, right? Then you start thinking about higher level languages, and the closest you can get to the machine at that point is really C++, which also has a semblance of earthly human-like languages, right? So we learn C++, and the reason we learn C++ is because we know how much effort is taken by the CPU to do something you want. That's why the best managers you can get out there, right? Out there, the best manager, once you guys start working, right? So the best managers you get are the ones who have themselves been individual contributors at some point, and they know what needs to get done, right? So if you have someone who's out of MBA, born with a silver spoon in their mouth, and because their dad went to some big college and they went to a big college, and that they're a manager without having to know what needs to get done, they're a really shitty manager, right? Because they don't know what the hell needs to get done. It's because they're like people who refuse to learn C++, and they just come in with a higher level language, and they know, right? Things just get done, right? And I'll get it done because these resources, because from that person's perspective, the manager's perspective, all these workers are just resources, right? To be shuffled, right? In and out, in and out, in and out. So if a particular resource takes more cycles, more work to get something done, this manager doesn't really care, because it's a resource that is delivering on what it is promised to do, right? So it doesn't care if it's doing it log linear or linear, because I don't care, because as long as it's Monday morning, I'm going to get the result from you, right? So, and that is a really mean outlook, because that's really not a good manager. A good manager is a humanitarian manager, is a compassionate manager, who's also lived the life of all these other people who know the struggles they're going through, right? So C++ prepares you like that, because you now know what the CPU is actually doing, right? So when you ask for memory willy-nilly, right, and say, well, I want to get like 10 terabytes here, right? And CPU says, what do you want it for? Right? It never actually asks you, right? So that's the beauty of it. It just gives it to you, right? And you leave it hanging around and someone else, your fellow programmer, right? So on the next cubicle comes over and says, well, you want to do some sorting here. How can we do this efficiently? And you say, hey, you know what? I got like 4 terabytes of memory locked away. I'll give it to you. And it's just, oh, you got 4 terabytes of memory? How did you get it, man? Right? Yeah, when we started out, I asked the CPU for 4 terabytes and I locked it up here. So I got a lot of memory. Anytime you want memory, you can come and ask me, right? And then the guy says, are you crazy and out of your mind, man? Because of you, everybody else is trying to be efficient, because everybody else out here has no memory, because we asked memory, CPU, and says no memory, out of memory, because all the memory has been given to you. So you're the reason why we don't have any memory, right? So that kind of thing does not happen, because in C++, you know the real cost. You know the real cost. You know all these other people. So you're not living in a bubble of your own. You're actually living in the whole world, right? So you know what the CPU experiences. You know what your fellow programmers experience. So you get a more holistic view of how a programmer designs their product, right? So and that's the reason why when you look at Java code, right? So forget about Python and JavaScript, even Java code. Because when I usually, right, not all the time, but I can tell when a Java programmer has no idea of C++ or even what goes on underneath the covers, because because Java, unfortunately, masks masks the complexities of object creation, you know, on the heap anyway, right? From you, in a sense, not object creation, right? Memory allocation, because they've got a servant following you around, right? So the servant is your garbage collector. This is in Java, it's called a garbage collector. And so what Java says is that, you know, you're such a busy guy, a master programmer, who knows everything, right? So I don't want to burden you with the task of allocating memory and deallocating memory. So you just ask and I'll give it to you, right? So that's what all these higher level languages, that's what they promise you, that you don't have to explicitly do a new, actually, I don't know, we're talking about new and, is this useful? This is just like two lectures down, right? We're going to talk about memory allocation. Is that useful? Or we'll just go out to code today.
Maybe, can we just move on?
I'm sorry. Thank you.
You've been talking for quite a while.
Right. So let's pick up the code. Let's pick up the code that someone wrote last class. I think Nate managed the code. So pick up the code and we can do that. So there's a couple of.
Still, it's a good point you make, you know.
Yeah. We'll come back to that later, right? We carry on this conversation offline or email in the chat. That's cool. Fine. All right.
So you're saying that because, you know, that C++ is a good starter language because it kind of helps you understand how the computer works.
Yeah.
Absolutely,
Chad. I
totally, the code is compiled, right?
Yeah. We can talk. We schedule another lecture if you want.
I know something interesting.
We'll talk about
it. Actually, it can help you. Sometimes you can even view compiled code under a debugger, and you can kind of understand what's doing assembly.
Absolutely.
But you can't do that with Java.
I'm sorry to interrupt you, Chad, because I want to decide who's going to take the screen, okay? Because this conversation can happen later too, right? I'm sorry to interrupt you. Hey, who's going to take the screen, right? Someone take the screen. It doesn't matter if we do the same code as last class. I don't have to bring it up, okay? Don't have to bring it up. We'll code it from scratch, right? We'll code all the functions we talked about, I think. Or you can bring up new functions, right? So we can code it up it class. And also use that to talk about, you know, recursion in general. What time is it, by the way? Yeah, 8:20. Yeah, it's around time. 8:15 is when we start our class, right? Until one is just doing, you know, friendly banter. Oh wow, we've got a lot of students here. Why is nobody picking up the screen? Do I need to call out someone? Hey, someone volunteer. Just pick up an editor, right? I'm going to call the code, right? Or Nate or someone else is going to call the code. You don't have to type anything, right? So we'll just call the code. You just need to, you know, function as typist. Can someone do that? I'm actually not looking at chat. Wait a sec. There's 2 messages in chat. Well, Nate actually stuck the replete link, but you know, we'll open a brand new editor. Well, that doesn't matter. We'll just code from scratch. Okay. We can leave that alone, right? Leave the one from last class alone, and you can compare. Maybe that's a completely different approach.
Right? Well, I've already taken the screen before.
Yeah, Peter, no worries. Take the screen. That's fine. Yeah, I think it's quite a while since you. Yeah.
That's true. All right, and then what would you want? Here, I guess I'll just pull up the play.it from before.
No, we'll just do a brand new code, brand new
code.
Template. Yeah, brand new template, right. and we'll do. And we can code it all up within a half hour, I think. Hopefully.
All right, so dishes. This is the code from before. I will make. Here, I'll just do reply to it. I'll make a new one. I don't have any new one. Oh.
No, it doesn't matter. You can just copy and paste the whole thing into some shareable window later.
All right. Well, we have this.
Great. Okay, cool. All right. So let's see. Again, so here we're talking only about recursion, right? We're not going to bring classes and all these other things into here. So we'll just keep it lean and only about recursion. So what we were talking about was, you know, we picked a couple of different couple of functions and we implemented that recursively and non-recursively. So let's just do the very first one. I think it was a sum of the first 10 integers, right? Sum of the first 10 integers. So above main, go type and say, yeah, type in we'll do is int, say size t, size t sum underscore n underscore iterative, right? And then pass an n, which is also a size t. And then we'll just do the one-liner so that we can compare and contrast with the recursive version. Yeah.
Like that.
So, on the next line, we basically say for size t I equals 0, I less than n, I plus plus. In fact, you can start at I equals 1, right? So it doesn't matter. Yeah, I equals 1, I less than or equal to n, less than or equal to n, and I plus plus. And then above the 4, declare a size t accumulator called sum, right? Size t sum equals 0, sum equals 0. Yeah. And then on the next line after in the 4, inside in the body of the 4, you say sum plus equals sum plus equals.
Oh wait.
Yeah, sum plus equals I. Right? Okay. Now that's it. That's it. And then yeah, in fact, you don't even need the braces because it's just a one-liner 4.
Yeah.
And then you can just return sum at the end. There's another way. There's another cool way to write the same thing, right? So I'll just do it in 2 different ways, right? A couple of lines down and say comment, return sum, and then a couple of lines down, say comment version 2, right? Comment version 2, right? So yeah, do version 2 of the same thing. Here we can do it using so you can pick and choose the flavors, right? This is pineapple and strawberry. Okay, so copy and paste the whole thing. We'll just change the for loop and the body of the thing, right? So body of the thing. Now, here, you notice, and it may be bad, right? So here, okay, so what we want to do is something clever. And it's actually version 2, and I also say clever hack, right? Unclever hack. Okay, so version 2 hyphen unclever hack. Unclever hack meaning it's a hack, recognize a hack and appreciate it, but don't actually use it in your code because it's not as readable. Okay, that's what unclever means. Okay, all right. So here, what we want to do is take advantage of the fact that n is actually not a constant parameter, right? So it's actually mutable. N changes, yes, n changes, and it's size t. So we're going to change the value of, and so we're not even going to create a new parameter called sum. We're going to change n to have all the values in it and then return it, right? So get rid of everything in there, get rid of everything, and we'll do a while loop, right? So and say space, yeah, while oh, wait. Oh, damn, we do need one more variable, unfortunately. Yeah, okay. Well, you know what? It's not an unclever hack anymore. But it's just a variation. It's not an unclever hack, okay? So yeah, introduce a sum variable, sorry. Introduce a sum variable. Sum equals n this time, right? Sum equals n, right? Sum equals n. Size t sum equals n.
Oh yeah.
We'll make it different. It's slightly different anyway. All right. Okay. So now you say while yeah. Okay. And then yeah, variation, and get rid of the not very readable because it's not very readable anymore. All right. So now we say while n greater than 0, right? Sum plus equals n. Right, and you can actually say it on the same line too. Space sum plus equals n. Sum plus equals n minus minus. N minus minus. Yeah. Okay. So what this basically does, actually, it's sum was already n, right? So so this is a corner case we need to fix. So while sum is n, so the next thing you want to add is n minus 1. So it should be sum plus equals minus minus n, not n minus minus.
Yes.
In fact, yeah. In fact, no. Put the minus minus here. While minus minus n greater than 0, right? So minus. While while. What happens if you get past 0? So you want to say while n minus minus is greater than 0, right? So while n minus minus is greater than 0, which means if you get past 0, because size t can be 0, right? So after you do the minus minus, it's going to be a big ass number. And then the while loop will be like practically infinite. So what we want to do is test it before and say if it is not 0, then we decrement it, and then. All right, you know what? Scrap this method because there's too many corner cases and I don't want to waste time. No, don't scrap it. But say fix the corner cases here. We don't want to go into the detail on the comment. There's corner cases we need to go. Yeah, we can fix it later. We can come back to it and fix it because I want to talk about recursion. So let's just skip this for now. There's corner cases that you need to run through in your head and make sure what happens if n is 0. Does it actually get all the numbers from 1 to n? All those things you need to run through. But it was a 4K. So you see the trade-offs, right? Because in the 4, it's actually slightly more verbose, but it actually is very clear what's going on, right? In the while, it's still is clear, but there's corner cases you got to work out. So you see the subtle advantages between the two kinds of loops and disadvantages, and so you start thinking about these things. And it is very similar when it comes to iteration and recursion, right? So now let's do the recursive version of the sum, right? So let's do the recursive version of the sum and say, sum and recursion. Sum and you already called it recursive.
Let's do that because it's just a variation.
Oh, I see. Yeah. So make a recursive. Sum recursive. All right. And here, if n equals 0, just return 0. If n is 0, return 0. And here is where you don't need some extra variable, right? Because your variable is going to be carried through for you automatically in stack, right? So you don't need that sum equals n there. You don't need that size t sum equals n. If n equals 0, return 0. Else return n plus sum n rec return. No, you don't need a return. You don't need an else, right? Else just say return.
Oh, I got you.
Yeah, return. In fact, what you can do is put the first return on the next line and push it into the if, so that it doesn't look like the second return belongs to the first if. Yeah, hit enter there, and push it in two characters. Yeah, okay, all right. So now it doesn't look like the second return also belongs to that if.
Gotcha.
Yeah. All right. So now return n plus sum n rec. Sum underscore n underscore rec.
Yep.
N minus 1.
N minus 1. Okay.
Yeah, so that's basically it. That is a recursive version. It's only 2 lines, right? It's only 2 lines. In fact, you can turn this into a ternary operator too, right? So I'll show you how to. So on the next line, let's do the ternary operator inside comments, so that right? So it's on the next line. You say on the next line within comments. Same thing using ternary operator, right? So on the next line, enter. Same thing using a ternary operator. Ternary is, I think, is a T. No, not Turing. Did you try Turing? Okay, ternary.
Ternary. My bad.
Yeah.
I think it's a TERNARY.
TERNARY. Ternary is third. Third, I think. Ternary is
gotcha. Ternary operator.
Yeah, ternary operator. You say return. On the next line, you say return. N question mark. Or make it a Boolean. N equals 0 question mark. N equals 0 question mark. N double equals 0. Double equals 0. Double equals 0.
Oh yeah.
Is 0 question mark. Yeah. And then separate the operator from, because you have spaces around the equals. I have spaces around the question also. All right. So equals. So if it is 0, you just return 0 on the first 0 there 0.
Okay.
And then colon, and then 1 colon, and then space, n plus, sum n rec, n minus 1.
I see.
Yeah, and then I believe everything there. Maybe you don't even need braces. Yeah. I think that should. Hey, mouse over. Why does it say green? Why is it green underline?
Unsequenced modification access.
Yeah. I think what? No, not some n minus 1, not n minus minus. N minus 1.
Oh yes, I understand.
Because it otherwise passes the number before it's subtracted, right? If you do minus.
No. What it says is that because you have n minus minus, it's not really sure whether you mean the n minus minus to happen before the n on the left hand side. N plus, right? That n.
Yes.
Or just in here. So it's not sequenced properly. That's what it means. Because the a plus b. Because of the plus doesn't specify which needs to be evaluated first, A or B. All right. So
I mean, otherwise, like if you did minus minus, it go infinite loop, right?
Sorry?
If you did minus minus, it would keep going an infinite loop, right? If you called the function with
No,
that.
no. It's not related to that. We can absolutely talk about that later, right? Absolutely, Chad. You hang on to that point.
Cool.
Right?
Maybe I can experiment with that later and copy the code.
You mean put the n minus minus there and then run it?
Yeah. See if
No,
it makes
there's
sense.
nothing. No, it's not gonna matter, because what will happen is it's going to call. It's going to n minus minus. It's going to minus decrement n, and then pass the value, right? It's not going to matter. All that the compiler is saying is that the value returned may not be guaranteed to be right, because with the n minus minus, I cannot guarantee if it's going to happen before the function call or is even before the n on the left hand side, n plus, right there. So that's what the compiler is saying. I don't know. It's not specified in the standard which one should be evaluated first. So I can't guarantee. So that's what the green underline means. Let's not go into the detail, right? It's not so important, right? So n minus minus, but you can actually experiment and find out. In fact, this is actually a very rich discussion point in the Reddit forum, right? You can say, hey, we talked about this in the lecture. It's the n minus minus here. What's going on? This is going to be an infinite loop, right? Post a snippet in Reddit and have a discussion there, and I'll also participate. Yeah, is that good?
Cool.
All right, cool. All right, so yeah, you can comment out the tertiary operator.
So I can probably experiment with it and tell you everyone what happens.
No, you can share your findings and say, hey, this is interesting.
That's what I meant to know, like what happens if you do n minus minus of this code instead, right?
Yeah, or you can't, because it's such a simple experiment. You don't have to post the question and ask other people to solve it. You can say, hey, I tried this simple experiment and I find this is the answer. I'd be interested if someone else has a variation of this or tried something else, right, similar to this, or something like that, right? So other people also share something similar, rather than saying, hey, what is 2 plus 5, right? Who's going to answer what's 2 plus 5, right?
Yeah.
All right, cool. All right, so you can comment out the tertiary operator, but that line 28, because that is basically another way, not tertiary operator. What was it? Ternary operator, right? So we can comment it out, because that's another way of doing the same thing. That's essentially what it is, right? So and you can do the same thing. It's just one line. So that's a recursive version. So that is basically the recursive version. Now, what we can do is forget about factorial, right? Everybody does factorial all the time. But here's an interesting challenge for you to solve. Maybe you can solve it in the forums, right? You solve it in the forums. How many digits programmatically, right? Write a computer program to find out how many digits in base 10. It's a base 10. So to make a note of this problem, right? So maybe someone even posts a question. This is a question that was asked. How many digits does the decimal representation of 1000 factorial have, right? 1000 factorial, right? So 1000, everybody know what 1000 factorial is? Right, 1000 factorial is 1 times, 2 times, 3 times, 4 times, all the way up to 1000, right? So how many digits does 1000 factorial have? How individual digits? So that's a question, and you can use a computer program to find out. So maybe someone write a program and share it in the blue subreddit, right? And say, hey, here's an interesting question that came up in a lecture, and here's an interesting way to solve it, right? So you can try and check these out. All right, so we won't do factorial and stuff like that today. Let's just go to Fibonacci directly, and then when we do Fibonacci, after we do Fibonacci, I can talk about how. We'll just do the recursive version of Fibonacci, right? Recursive version, and then we talk about why is it a good idea, is it a bad idea, or what the advantages, and then we can talk about why recursion versus non-recursion, and so on and so forth. Is that okay with everybody?
Did we do this last class though? Recursive Fibonacci sequence.
I'm sorry.
Didn't we do this last class? I think
Yeah, I think we did. I remember that.
Yeah, we did. But
right. Did you also get to talk about the efficiency of Fibonacci and why it takes long and what's going on and so on and so forth?
We talked a bit about that. I was actually a little curious about that because I know Fibonacci is a common. I know Fibonacci is a common example for recursion, and to me at least, it seems like the reason why is because in order to do it iteratively, you have to sort of understand the entire problem and understand what happens through each loop in order to code it out. Whereas the Fibonacci one, you just kind of make a if statement case and then return just what the Fibonacci's definition is. The Fibonacci of a number equals the Fibonacci of that number minus 1, plus the Fibonacci number of that number minus 2. So logically, you can just write out the recursion much like the formula itself, and it'll just solve it. Whereas this one, you have to do a lot more of the nitty gritty details on your own. And so you have to actually know those nitty gritty details.
So yeah, the recursive one actually looks a lot more readable. In other words.
But we mentioned it was less efficient, the recursive one, because
Yeah, that's what I mean. You know, it is a lot less efficient, but you know, most of the
when
time,
you run
you know,
it, you can see it.
Why is it a lot less efficient?
It
Because
makes
you're-
sense. Oh,
Because you're, you know, each one of those minus, you know, the recursive, it breaks down into like a huge tree of calls. Because he has to recompute the values like n-2 and n-1 again. Whereas you don't have to do it if you do it iteratively.
like our line 70, was it 74?
Yeah,
I think it was.
75. Yeah,
Okay.
75, I think.
It
Yeah,
calls
'cause-
itself twice.
Yep, and then each one of those calls will end up calling itself again with a -2, -1, and so you're actually repeating the same calls for, you know, for all the whole entire values of the Fibonacci.
Right.
well, and likewise, for a while, you're actually running each, I guess I'll call them an iteration. In each iteration of the method while you're running through this tree. So as it runs through your first one, so Fibonacci of n, I'm not going to call it the actual name, but like you're going to end up looping into Fibonacci of n-1 and n-2, and then you go through all those. I'm not going to finish writing them out. I'm not going to finish explaining those either, really. But you end up, until this one at some part down here ends up actually returning something that breaks back into its previous one, then all these will start closing. But until then, all of these methods are still running, correct?
Right.
Yeah.
Right. Yes. So that is the overhead of the recursion. But you know, someone else brought up something that it's not just the fact that all these methods are in cryogenic state, right? It's basically that's what it is, right? Until it's been released, they're in cryogenic state. They're frozen in time until their descendant comes back. This is basically there. It's not gone away. It's there. That's what you're saying, Peter, right? Because if your recursion is when this calls this and this calls this and this calls this and this calls this, right? Fib of n, n-1, n-2, and so all the way until this guy returns, right? All these guys are not free to go. They just have to be there, right? They have to live. And yeah, they're still there in cryogenic frozen state.
But I think what Peter was trying to explain was more than that. I think he's also trying to explain that even though they're in cryogenic states, they're branching out into more children calls. Like for example, let's say you start with Fib5, right? That's the original call. Well, Fib5 is going to break down to Fib4 and Fib3. And then Fib4 is going to break down to calls of Fib3 and Fib2. And then Fib2 is going to call Fib0 and Fib1. And then
Oh, his mic cut out.
Is everybody following along this discussion?
Yeah,
Right?
I'm following
it's
along.
easier if we draw it. I think it's easier if we draw this picture.
Yeah. But I want to make
picture?
sure.
Oh yeah.
Yeah, you get to the whiteboard mode.
But well, I'm noticing the exponential, like, you know, calls and functions, the bigger the number.
Right. Hey, I want to make sure everybody's on board. Okay, it shouldn't just be like the five of us.
But we did talk about this yesterday, so
But is everybody
it's
comfortable
still
with these
people.
ideas, right? Is the important thing is everybody comfortable with
I'm
these ideas?
comfortable, but I'm going to, you know.
Hey, not you, Chad. Okay, not these five guys. Okay, not the five guys who are active every class. I want to hear from someone else who's not comfortable with this, actually piping up and saying, hey, you know, this is all Greek and Latin to me, or I don't understand anything, right? So someone has to say something like this, right? Otherwise, how would we know, right? How would we know? This is a bunch of people who, and to make matters worse, there's these five people, okay? There's 5 or 6 people who actually know what's going on and they're actually following along. And so I'm surrounded by an illusory crowd. I'm surrounded by just my yes sayers, okay? No sayers are far away, you know, like a president of a country, right? Who has a cabinet who everybody agrees with them, right? So I'm just surrounded around it, and I just move around. Everywhere I go, these guys, every lecture, these 5 guys are there, right? So they're my satellites, the sun and the satellites, right? So well, no, I can tell if the other people understand or not. How do I know? Someone has to pipe up and tell me, right? Because otherwise, and then at the end of the class, it doesn't make me very happy to see that, I got 40 students and then only like 10 people passed, or 10 people got B+ or better. How much fun is that to a teacher, right? So it's only fun if everybody has a great time and everybody has actually got the skill and they can do things with it, right? It's not just these 5 people. So someone has a problem, this is your chance, right? So please do say, because I know we're talking about recursion and how many times each function is called and all these things. These are important, right? So it doesn't matter. And like I said before, CS2A, you'll pass for sure. Right? Most people will pass, unless you've been totally absent, you'll pass. Absolutely, right? Only 2B and 2C gets hard, right? But in order to be a strong candidate in 2B, you should basically pipe up and ask here, right? Don't depend. I know a lot of people, and I was like this a long time ago, right? So when something is hard, I say, well, I know enough to pass. I'll just get a pass mark, but I do need to know this, so I'll master that afterwards without stress during the holidays, right? During the holidays, I'll just sit down and master it. Never actually works for me, right? So I found after like 4 or 5 summers in school, I found it never actually worked, because the next year I go back and I found, that I thought I'd teach myself, I never actually did, right? So I start with a handicap, and then I have to catch up. And so that kind of thing never worked for me. I think that may not work for you too, right? So don't think that, well, that's an interesting concept, but I'll come back to this after 2A and teach myself that. No, this is your best opportunity to teach you. So everybody's here, like all of us trying to teach you. All right, so you decided not to draw this. You want to do this on screen? I basically talk through this too.
Someone can draw it and then maybe post it in Reddit or whatnot. That's just more so a note of like how it works, I guess.
Yeah.
And then so
Someone
Susanna
said,
had
Susanna said something.
You wanna?
I was just gonna say, since we're doing Fibonacci, when it's the Fibonacci recursion, there be like some kind of base case where 0 and 1 are different from if it's greater than 1.
It's a good question. Actually, so
I'm sorry, I totally missed the question. What was that again?
I was saying, if we're doing Fibonacci recursion, right?
Uh-huh.
Wouldn't there be some kind of base case where it's different from what we're getting? So Fibonacci n-1, wouldn't it, like, if n was 0 or 1, wouldn't it be different?
No, Fibonacci is defined to have the same value for the first 2 numbers. The first 2 numbers are, in fact, it doesn't have to be the first 2. The first 2 numbers are 0 and 1.
Yeah, that's what I meant.
Yeah, the first 2 numbers are 0 and 1. And I think, who was it? I don't know who quoted this, but someone took advantage of the fact that, that if Fibonacci of 0 is 0 and 1 is 1. And then the next number is basically 0 plus 1, which is 1. So you actually get the real number as a sequence. Because if my memory serves me right, my Fibonacci series started at 1. There's a 1, 1, and then, right? And that always seemed to be quite, artificial to me. But this seems to be so much nicer, because you have 0 and 1. This is a natural start.
Yeah.
The sequence, and everything else is basically some of the previous 2. Yeah.
Actually, we also looked up that Fibonacci sequence has negative side too, if you really wanted to.
I'm sure. Just like
it's kind of crazy.
Has, yeah. Even for factorial, right? The gamma function is basically gives you factorial of fractional numbers, right? Yeah. It's interesting that Fibonacci has negative. Thank you for bringing that up. But I didn't know that actually. So but I would have expected that, but I didn't know that. So that's very interesting. Thanks for pointing that out.
Yeah.
But someone was going along the discussion was going along the route of how 5 has repeated calls to the same thing, right? So you're calculating the same value more than once, right? So someone was talking in that direction, and I interrupted. I'm sorry.
I don't remember.
I think Robert was saying it is not just the stack overhead, because Peter said it was a stack overhead because all these guys have to be in cryogenic frozen state and can't be released until they return. right? And then Robert said, no, that is definitely overhead. The stack overhead, but that is not the biggest overhead in Fibonacci. The bigger overhead there is basically that certain things get calculated more than once, right? Because if it has to be calculated exactly once, you can't do any better. Like, in CS2B's question number 1 is basically an exponential problem, but it's an exponential problem unlike Fibonacci, because in Fibonacci it's exponential, but all of the branches have overlaps, because you're going to be calculating Fib2 more than once, right? You're going to be calculating Fib2 here, Fib2 here, Fib2 there. So Fib2 is going to be calculated an exponential number of times. Same thing calculated. That is what leads to the exponentiality of Fibonacci, right? Whereas in CS2B, Michael Losef chose this quest. Actually, this is very interesting. I still haven't finished wondering at the beauty of this particular choice, because it is also exponential, but it is not an exponential algorithm like Fibonacci, where the exponentiality or the exponential nature of it is due to the repeated recalculations, right? Repeated recalculation, basically overlapping space. There is no overlapping space, right? But it's still exponential, meaning the search space itself is exponential. Right? Fibonacci, the search space is not exponential. That's why you can do it linearly, iteratively, right? Whereas here in the subset problem, it's a power set. The power set is the search space, is exponential, 2 to the n subsets, right? So it is impossible, right? It's mathematically, logically impossible to actually examine every single thing using some technique like Fibonacci. You cannot have. So that is what the beauty of dynamic programming is, right? So you'll hear this term bandied about a lot, right? People talk about dynamic programming. I don't know if you're in LeetCode and doing competitive programming, or if you're interviewing at some of these big software companies, they expect you to know about dynamic programming. Dynamic programming is nothing, there's no magic to it, right? Dynamic programming is basically just recursion, or any kind of problem where you have to keep solving the same thing over and over again. But if the problem space is basically full of overlaps, like Fibonacci is full of overlaps, right? So many damn overlaps, exponential number of overlaps, right? Fib2 is calculated so many times, Fib3. So the smaller the number, the more times it has to be calculated. So when you have these overlaps, you can leverage that and say, well, if I got rid of this algorithm is exponential only because of the fact that there are an exponential number of overlaps. Yes or no? Right? It's a Fibonacci. So can someone verify that? So yeah. So Fibonacci is exponential only because of the exponential number of overlaps, right? Not because of the exponential number of search space, because the other problem is also exponential, right? It's also 2 to the n, but it is not DPable, right? You cannot make a DP out of it. It cannot be made a dynamic programming algorithm because there's no overlap, right? If there's overlap, then you can be a clever programmer and say, well, because there are overlaps, what I can do is anytime there's an overlap, I'll only calculate it once. The next time onwards, I'll just use the previously calculated value, right? Is that a clever way to handle an overlap or not?
Yes.
Right?
So,
yeah. So that technique is called what in computer science?
Dynamic programming.
No, it's called caching. Right?
Oh.
So it's called caching.
It's the same way.
Yeah, when you calculate something really, really complex or fetch something really, really complex, but then you suspect that it's going to be calculated or fetched more than once, then you don't let it go, right? So web pages and browsers and servers do this all the time, right? They fetch a page, they cache it locally, because if you ask for it again, they don't have to go all the way back, they'll give it to you. So it's called a local cache. It's a cache of goodies. So
I think I saw this in my older computer science class as well, where they do complex operation over again, right? If it's done before, right, on the same thing.
Yeah,
that's basically
maybe. Right?
You
Same
don't
idea.
put in the cache number. You just give it to.
Right. So in Fibonacci, basically that's what you're doing, right? So you say that, when I calculate Fib of 2, I will basically check my cache to see if I've already done it once. If I've already done it once, I'm not going to call it again. Right. So same thing happens. Fib 2, understandable, right?
Cool.
Imagine Fib 55, right? And you want to calculate Fib of 57. For Fib 57, you need to calculate F of 55, right? So imagine if you had to call 55 every single time, every number higher than 55 was called, you got to call F55. Yes.
Cool.
Right.
So I thought of an idea for this recursive Fibonacci. Fibonacci. Maybe we can create a cache value that, if it finds that it's already that, will just give it to you in the number.
Yeah, exactly. So you can do it in all these ways, right? So you can do it in all these ways. So you can maintain the cache, basically an array of, this is an array of n integers, right? So this is Fibonacci 1, 2, 3, 4, 5, 6, and so on. So every time you need to calculate the Fibonacci of anything, you look in the array of all the numbers before it, right? And say, well, I need a fib of 7 and 6. Are they already calculated? Yes. Okay, so I'll just pick them up from the array. Oh, they're not calculated, they're -1. So I need to calculate that, put it there, calculate that, put it there. Then I'll take these two values. So the next time I come here, I just pick up those two values. Does that make sense? Okay, so that's one way of doing it. And so the next step you can take the optimization to from there is to say, do I need the whole array, right? So if I want to calculate fib of n, do I need to have an array of n elements, right? No, actually you'll find that I don't need n elements, because if I start from the beginning and march towards the end, then I don't need to keep all of those. I just need to keep the last two, all right? So instead of having an array of n elements, you can actually have an array of only 2 elements. Only 2 elements, right? So look at that, right? So how cool is that? Because then you're walking the array. So you're walking. So that is called table driven, right? It's not even array driven, it's table driven. It's a finite size table driving an infinite size problem, right? Because once you write that program for Fibonacci, it's like 3 lines or so, right? Iteratively. No matter, even if I ask you to calculate the Fibonacci of 10 billion, right? Your program complexity doesn't change at all, because you're just walking, right? Walking, you're turning that array and bam, 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 bam. So 2 at a time, and I'll just do it in linear time. So it doesn't take any more time, however big the number is. And except for, the number of times you have to do these arithmetic calculations. So that really is the beauty of recursion and dynamic programming. We haven't talked about stacks. We'll talk about stacks and so on later, but that's basically it. I don't know.
Professor, looks like so. I guess there's the other way to go around with this Fibonacci recursion, where most of the time, let's say we're asked to compute recursion, let's say Fibonacci of 5. I guess we could be asked that, and then we go the other way, which is we start with calculating 0 term and 1 term first, and then send that to the recursion again, and then calculate the next terms.
Yeah.
And that way you don't have to do dynamic programming at all, right?
No, that is in fact dynamic programming. If you think about it, that is in fact dynamic programming, isn't it? Because the dynamic programming is table driven. Right?
I see.
Yeah, because it's table driven. It's dynamic. So dynamic programming can be done in 2 ways. You can do DP using recursion. You can do DP using anything you can do in recursion. You can do in iteration, vice versa. Most of the time, right? So I think very exceptional cases where you can have a 1-to-1 translation, right? So, so DP can be done in 2 ways. And if you go to an interview and you do DP using recursion and they say, no, you got to do DP only using non-recursive iterative methods, that interviewer doesn't know what they're talking about, right? So DP can be done in both ways. So the way you do it in using recursion, the common name given to that kind of DP done using recursion is called memoization or ledgerization, right? Memoize or ledgerize, right? So ledger is a huge book where you keep stuff, right? And a memo also is something that you write down and leave, right? Somewhere, so you can pick it up, memory. So memo. So it's a memoize or ledgerize. Those are the 2 terms. So that's basically, you're going to still do recursive Fibonacci, but your fib, when you call your function Fibonacci recursively, it's not going to immediately call recurse again. Before calling the recursive version again, it's going to check the cache, right? The ledger or the memo that is written, right? To say, well, I've been asked to call, asked for fib 55. Does fib 55 already exist? Let me check my ledger, right? So it checks the ledger. Oh, fib 55 is actually -1, so it doesn't exist. So let me calculate fib 55. All right, so in order to calculate 55, I need to calculate fib 54 and 53. So here's a call. Recurse, call fib 53, recurse, call fib 54, right? Get the 2 numbers, add them together. Okay, that's a result. That's 55. I'm going to take this value, return it to the user who called me. But before he or she called me, before I give it back to that user, I'm going to take that value and replace that -1 in the cache, right? In the memo, right? In the ledger. So I'm going to take that. So next time they come and ask me, what's fib 55? I don't need to call these 54 and 53 again. I can just pick it up from the ledger. Does that make sense?
Yeah, I see what you say. So I did a quick Google on memoization and dynamic programming. So I guess one is coming from the top down and the other one's coming from the bottom up.
It's exactly
like
the same.
Saying.
It's exactly the same.
I see.
Yeah?
Yeah.
Oh, Peter. No, Peter. Cool. Yeah. All right. So what was I saying? Right. So fib and recursive. So yeah. All right. If you guys have any other questions, we can do it. So we've done fib and recursively. Do you want to continue talking about it or implementing more versions of Fibonacci? Or again, can you start talking about stacks and what goes on when you do the recursive call? Because when you do the recursive call, there's a bunch of magic that goes on in the background, right? So just like when you call any other function. So we can talk about that. We can talk about mathematical induction if necessary, because math induction is very closely related to iteration. Let's say recursion. Many ways. So many different commonalities. I can talk about that if you want, right? So math induction and recursion. And then we can talk about stacks, because stacks play a very critical role in recursion and how recursion unwinds and so on. Yeah?
Yeah,
Yeah.
stacks sound interesting.
I know
because,
personally, yeah,
You wanna talk
personally,
about-
I know I know exactly what you're talking about when it comes to the first couple of terms you're talking about, but when you start speaking about how recursion is going to apply to our stacks, I have a vague understanding of how that will work, but I don't think I've ever done it myself, if that makes sense.
Sure.
That
Sure.
would be
Oh,
interesting.
no. I think, Peter, you got it the other way around. I was saying how stacks are relevant to recursion. What the role played by stacks, the computer stack, the program stack, right? Not the
Yes.
stack that we implement, right? So we get a free stack every time.
I understand now.
So that stack, what is the role played by the stack? And yeah.
Okay. I could see it, but yeah,
we
I've
can do
never really
that.
implemented something like that before.
Yeah, or you guys can continue to talk about Fibonacci, other ways of implementing it, and interesting. You were having an interesting discussion before I just butted in and hijacked your, conversation. So I'm sorry. I'm sorry. So you guys, you should feel free. What time is it now?
It's only 9.
Oh, it's only 9. We got a lot of time. So you guys should feel free, even if you want to talk for 10 minutes and then, rope me back into the conversation, I'm fine with that, right? But when I come back, we can talk about why stacks are used and, what is the use of a stack? How many different stacks are there? So there's the operating level stack, there's a program level stack, and there's all these different stacks, right? So let's talk about where, and what stacks are. And then that'll take you into implementing a stack ourselves, right? We'll implement a stack next class using dynamic memory, using new, right? Allocating memory. And that's why I was going with this before, because in chat you interrupted me, right? So yeah, C++. Why is C++ so good? Because in C++ you don't get a servant, right? In Java, in all these other languages, every other language, you just grow up as a spoiled kid. Right? You just grow up on a rich, with rich parents, spoon in your mouth, right? Silver spoon in your mouth. And you say, well, you can take and use anything you want. When you don't want it, just toss it. We got a bunch of servants that'll come and pick up your garbage for you. That's essentially, right? So and suppose you grow up like that, you lack an appreciation of the difficulty in procuring things at all. So that also is unfortunate, because then you lose the ability to appreciate it, right? Or enjoy it. These things just become invisible background color for you, right? So if an iPad was basically part of your life from your birth, right? It's not even an iPad anymore. Because you only notice it if it's missing, right? You don't notice it if it's there. And so like that, you have a servant like in Java. Is Java is your first language. JavaScript is your first language. And you say, I'm happy. I'm never ever going to learn C++. And you just be a sloppy programmer. Well, you don't have to be, right? You can still think. You can still think and say, well, this seems to be doing all this thing, but is it doing it the best way? Is it doing it the easiest way, right? So then you want to think and say, well, if it's not doing it the easiest way, so I need to find a way to make it easier for that, right? And I don't treat it just like a resource, as like a human. If I wasn't there in that shoes. So.
I just want to say, as someone who writes a lot of Python, like pretty regularly, ever since taking C++ and like delving into it for my hobbies, for like microcontroller stuff, I've developed a habit of like looking at my code and really thinking, can I lean it down? Do I really need all these libraries to do this thing that I'm doing?
Yeah.
Like, is it necessary for my algorithm at this point? Can I are there hacks that I can exploit? Because I know like a lot of the libraries I use are optimized for C. So like I'm always thinking about these things now. And I feel like I'm just a way stronger programmer for having delved into it.
The minimalistic life is bitten into your programming. The minimalistic, yeah. Yeah, I know. Maybe it's, I thought it was general, but maybe it's just C++ programmers. But that's not true. That's not true. Back at SRI, brilliant programmers all around. So I know a Java programmer, right? Doesn't know a line of C++. And in fact, was also very passionate about Java, so passionate that he refused to learn C++, but did not make that person any less a star programmer than someone who had mastered computer sciences, as far as I'm concerned, right? So they knew, right? Because you can talk to them in Java speak, but you can talk to them with the same freedom of talking to another C++ programmer, right? You know what I mean? I don't know, maybe you don't know what, maybe you'll know what I mean after you do C++, right? So when you talk to an experienced programmer, you can talk a lot faster. Because you don't have to explain certain things, right? Certain things you can just take for granted that they know, right? So you say, blah, 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 blah. You know, like two aliens talking to each other, because they really, that's what it is, right? When someone from a non-computer scientist looks on, right? That's what it looks like. But you know, but really high level conversation is happening, but happening in chunks that don't make any sense to other people, right? So and you can do that with an experienced programmer, but this guy didn't know any C++, right? But I could basically talk to him in Java speak. In any damn concept that I would talk in great detail in C++ or machine language to someone else, you know, you just understand, but you not. But so there are reasons, right? There are reasons that people choose a particular language for a particular thing that they want to do, and they become masters at that, right? So that's completely different. So, but I'm not talking about these outliers, right? So, you know, but for most of the people, I think if they're a Java programmer and they self-taught Java programmer, they've basically you got to be careful, right? When you're interviewing people like that, you got to be careful that, well, yeah, okay, they could be a Java programmer and they could be self-taught, that's fine. They could still be a good programmer, but let's just make sure, because they don't know C++, I want to make sure, right? I want to cover my bases and make sure that they actually know what's involved in keeping a program lean, right? Not just the look of it, also, you know, maybe the runtime of it. But do they know what's involved in creating an object? Because when you look at these programs written by the people who don't know the difficulties, this is allocate objects and deallocate willy-nilly, right? So, and they don't, they say, yeah, I get it for free, man, I get it for free, right? So no, that's not the reason. Just getting it for free. So and I think, yeah, thank you so much for sharing the thought. Yeah, maybe it's just C++, but yeah, that certainly encourages the way to program in a lean way.
Would the Java programmer, would he know how to lean a program because he's learned a method to lean his programs like manually in Java, or because he just understands the process of it, even though he's never had to lean code himself because the Java?
No, I think this is what happens. And thank you for asking that question. It doesn't matter which language you take, right? So doesn't matter. I think the danger really is only when, you know, when the first few years of irrational exuberance after someone thinks they've mastered a language, right? And if that language is not C++, it's Java. But, you know, someone who's really passionate about any language, right? Python, JavaScript, right? If they're really passionate and they keep doing it and thinking about it and see, and they wonder, well, you know, I write these 5 lines in Java and something happens, but how is it actually doing it? What's going on? They're bound to think, right? So what happens is that no matter, even if they don't know C++, if they're stuck at Java or JavaScript long enough and they thought about it and they're brilliant, right? They would basically come to the same conclusions as any other computer scientist, right? And then they become like this other person I'm talking about. So they know what they're talking about, right? So I think the essence of computer science will eventually come to you no matter what language you take, as long as you keep at it. But C++ kind of forces it down your throat from the word go, right? Yeah. Whether you like it or not.
Yeah, because I know personally, it's my dad's a Python programmer at heart. He knows how to code in a lot of the other languages, but he codes in Python. That's what his preferred method, I guess, is. And while I'm not experienced enough to have picked a language on my own, I've coded the most in Java. So as long as he's speaking to me in Java terms, it's sort of like, oh, I understand relatively what he's talking about. But things that pretty much apply to C++ or Python, things like choosing to allocate your own memory, like not the process of leaning itself. I understood how Java does that, but I didn't understand, or I didn't know, obviously, until I started taking a language that I could do it, that you could just choose what like the size of your integers, or you could choose, or when you allocate memory something, you yourself have to allocate the memory and then also manage that memory. You have to clean it up yourself. You have to do pretty much everything yourself. And there's all these things that Java does for you that I knew Java did for me, but I didn't really rationalize what it meant to do it myself.
Yeah.
Still don't, because I haven't really branched into that in C, C++, but that's my own.
That's right.
experience.
That's why I think that C++ helps people that go on to learn Java, because they know what it's like to live without a servant, right? So the best people to have servants, the best managers are those who have had managers themselves, or don't have workers working for them. They have to do all the stuff themselves. That they will eventually, they'll know, right, better. I think that's. But once there are other people, right? So who've actually picked up like your dad, right, about Python or Java, and they've learned, that's been there, and they've been in that long enough, right? They've been in it long enough that they've actually come to the same conclusions anyway, right? So through another route. Or maybe he did learn C++ a long time ago and then used that to get into Python, and then started using Python so long that he forgot that he originally learned C++, right? So that's the beauty of the Bay Area, I think, Silicon Valley. And I think it's going to be the whole world, right? In the next 10 or 15 years, because of remote work and everything being so possible and online. And so I think it's going to be the whole world, really. But out here, I think there's a lot of people, parents, elders, friends, who are really good at programming and computer science, that I don't know, in a way, teachers have it easy, but it's great for the students. It's great for the students because they have so many people they can go and get help from. And of course, in my courses, that's not allowed. Well, it's allowed to get help, but you just can't ask them for direct help on your Quest code, right? So you can take your Quest code to your dad and ask them to debug, right? So that's not allowed. But other concept-wise help, that's fine. Also, 2B and 2C, I think some students they want lectures. And it's harder to give lectures on concepts because you tend to assume that they know all these things. So I think when you guys go on to 2B and 2C, you can pick and choose concepts that you want Zoom lectures on, because they're just going to be online. I've always taught these courses online, except for a few times when I taught them face to face, right? So, but if you do want face to face lectures in my 2B or 2C, you just have to pick up a topic and then get a bunch of students who want to know about that topic, and I'm happy to talk anytime. Doesn't have to be a scheduled lecture. I'm happy to talk about that. All right, so you guys can go ahead, talk about Fibonacci if you want, right? Or anything else. Have a conversation. I'm just happy to be quiet, or I can switch off my video for about 15 minutes. Do you guys like that? I can switch off my video, go take a break, go look for Peter. I don't know where he's gone. But I can come back in 15 minutes. Is that a good idea? You guys want to play around with this code and have your own conversation for 15 minutes? Sure. Yeah. Okay, all right. So how about, and then when I come back, what we'll do is we'll talk about, what happens when you call a recursive function, what happens at the machine level, at the assembler level, and the CPU level, and where's the stack in there? Where's the stack, right? And with this call, return address, and all those things, right? And then parameter passing and all those things will start making sense too. All right, I'm gonna go on mute and video. I'll set the alarm. I'll come back in, I don't know, 15 minutes. What time is it now? Yeah. Alexa, set an alarm for 9:30.
Well,
right. What do we want to spend these 15 minutes on? Personally, I feel like we fully exhausted the subject of recursive Fibonacci sequence today and yesterday. Should we use stacks? Because I don't know what that is though, so someone else would have to get us started on that.
I agree. I think stacks are very interesting. I also think that
I actually I worked on that class myself.
Oh, good. Well, then.
Yeah, it's like, first in, last out, right?
Well, I don't know what stack is, so you tell me.
Oh, so stack. So this is what he was talking about. This is where I got confused as well. He's not talking about stacks, and this is why I think that he's going to be the one who talks about this when he gets back. But he's talking about the stack in your when you compile your program, you create a stack of memory, and you can manipulate that stack of memory away in C. And so we're not talking about creating a value of stack like first and last out.
Yeah, got it. I thought you were talking about that assignment.
Exactly. Yeah. No, I had the same I made the same misconception because I know what a stack is from Java. Where
That's
you,
like a
same
list,
thing.
right?
Well, it's the same thing that
But
you were
but
just
it's
describing.
except you know the lap. You can only like, for example, look at the top, right?
Well,
Unless you
that's the stack in Java, and you can code a stack any way you want. It doesn't have to be first and last out.
But
That is
I actually did that for you know, the C++. That's what I did on Quest 8. I was working on a stack similar how Java works it.
That's interesting.
You know, like how you can only access the top element in that one.
Yes, that is first and last out. That is a way of doing a stack. Stacks in themselves can do a bunch of things, but you know, it's covered probably somewhere. But that's creating a stack of variables within your code. He's talking about the stack of memory that is created when you compile your program, which works similarly. They're kind of related. It's just that one's created by the console and one's created by you, the coder. And it kind of, when you create a variable, it gets put onto your stack of memory. Like similar to how your first and last out program works. And then it will that's where until you find a place to store it, that is where it sits on your stack of memory on your compiler. I don't know the details of it honestly, so that's why I think somebody either more experienced or Anon himself should probably do a better explanation, but that is the understanding I have.
So it's
I
like
think-
our. Oh, continue.
Oh, I was gonna say, I think like, so when you create a lot of the you're creating memory dynamically, it actually goes in the heap, I believe. But your stack, when you have when you do like recursive, every time you call a new function, all those variables that were in the function that you were inside before need to get stored somewhere. So like your previous like n from your previous Fibonacci like function or whatever, those get put on the stack then. So the stack gets used for like when you do like new function calls and that. And
Yeah,
that's why you get,
that's right. When you call a new function, I remember that now.
And that's why you get like a stack overflows. Like if you go like recursively too deep because you overuse the stack and the stack becomes full, and then
Yes.
Yeah, I think the easiest way to understand, what's created where is, if you look at, we haven't encountered it because we don't have to do new so far. The keyword new, NEW.
Yeah.
Anytime you see a new that's created off the heap, and then anytime you don't do a new or malloc, MALLOC in C. Malloc and new both create stuff off the heap, and any other thing any other variable that you create, like int x or char y and things like that, these things are all created off the stack. Yeah, so if you look at the function definition on line 44 here, size tn, n is created off the stack.
Yes.
Yeah, and any other variables that you create, generally so far all the stuff that we created are pretty much off the stack. Yeah.
When you say new, are you referring to like an object? So like if I were to use the integer object, would that be?
Yeah.
Okay.
It doesn't have to be object. I mean, because
you can
character,
use the new keyword for.
Yeah, character isn't really an object, but I guess it is in C++ sense. But in C sense, it's not really an object. It's just a data with a memory, right?
Yes.
But when you could create actually like an array of integers using the new keyword or using memory allocation, malloc, and those are all created off the heap. Yeah.
Makes sense. All right. Well, looking at that. Oh, and I just realized fib and fin and recur. So I think we have exhausted Fibonacci. Is there anything about recursion, I guess, that we want to explore or talk about in general? We've got 10 minutes.
Is there max recursive depth? It's not too important, but sort of curious because they have one in other languages.
Could you repeat that?
Is there max recursive depth? Like,
That's a great question.
can you only, yeah, you know, okay, sorry, continue.
You're okay. That's, I think what Ryan was talking about is, if you, every time you, recurse into a new branch of methods, you're going to take all of your, variables from before your previous recursion, so size tn here, and it's going to go into your stack, the stack in your compiler. And, at some point that stack has a limit, and if you go over that limit, you get what's called a stack overflow.
I think there's some enforcement on the OS level of like how big a stack can get. I think it's something like 1 or 2 megabytes on Windows and something like 8 or something, or on Linux, something like that. It's like ballpark numbers. But at some point, the OS will try to protect itself by like limiting your stack. So like if you recurse too much, it'll
How much is that though?
Okay, I see. So there's no like explicit limits, just how big your stack is. That limits how many recursive calls your program can do. It sounds like.
Yeah. Trying to think if there's any like explicitly set limits. I don't believe so.
I know like in Python, there's like a hard limit of like 1,000 recursions or 1,500 recursions. You can look it up. Yeah, but I think in C++ is probably memory based, right? It's not how many times you can call.
There's a recursion like Linux or like a recursion. The default one doesn't.
Yeah, I think it's based on memory, probably not based on how many times you recurse. But like I said, it's like Python, which I'm pretty happy, I like programming in. And there is a hard limit on how many times you recurse. It actually counts. Yeah.
Okay, I see.
Yep. Oh, and even then, to set the recursion limit on Python, you have to make a system call. So you have to use the sys library.
Yeah.
So it is in some way like, so it's probably enforced on Python just to protect the OS, but the OS itself has its own limit.
Interesting. Okay.
Yeah. All right. And there's a bunch of solutions into there. That makes sense to me. Well.
Well,
yeah, I just did a quick Google. It looks like C++ does not have an explicit recursion depth count. Yeah, but it does have. I think it says like Windows by default is 1 megabyte.
Yep, I got the same answer.
Yeah,
Windows is on 1 megabyte.
So it's
Linux
memory
is on
size
8
based.
megabytes. Yeah, an operating system. They didn't say what Mac gives you, but it's a good question.
So you're talking about the call stack?
Yes.
The stack. The default is 1 megabyte for Windows.
Yes.
Yeah.
That's what we're talking
about. So
I don't know
what's
if
the
that's
stack for? Just give me a quick summary.
Well, that stack in itself is for what we've been talking about. Your call stack is for all of your
functions.
Well, it's for all of the variables within your functions. All of your returns, I believe, also go into your call stack. There's a bunch of things that go into your call stack. You can look it up. But essentially, and as someone else pointed out, if you're not going to use a new, or in C, there's a different keyword. There we go.
Matic, I think. Malik.
Yeah, Malik. Yes. MALC. And so we'll go with new. If you use the new keyword, it's not, your memory is not going onto the call stack. It's going somewhere else. So objects, for instance, there are other things that also use the new keyword, obviously, but objects is the thing that comes to my mind. And so if it's not using the new keyword, then most likely it's going onto the call stack.
I'm actually looking at the call stack right now.
Yeah, I think heap is a lot bigger. If you know, because 1 megabyte for stack sounds kind of small. Because like if you look at like all our programs that's running in our computer system, some of them can get up to like gigabytes, you know. And so I assume probably if the stack is only 1 megabyte, the rest of it's got to be heap maybe. Yeah. So heap could probably, if you do new, you could create like a huge data structure with new. But I guess stack is meant to be kept small.
Sure. So no, I have an answer. That was not my answer. I get it.
Right, bye, Aaron. Person. They said that to go. If we want to do some code, we could refactor or change our what is it, the Fibonacci, so it goes up instead of down. Because right now we have it going from finding Fibonacci of like 10, then 9, then 8, down to 1 or 0, and then it gives it back up. We could have it. Wait, could we have it? I don't know.
That's interesting. Good point. Let's try that.
It'd be more efficient anyways.
Could
I don't know how we
start
do it.
from anywhere in the Fibonacci and go reverse? That's a good question.
Yeah, so 0, 1, 2, and then we'd only have to do it once. But maybe we could still do that recursively. Maybe not.
Only thing is, how do I know when I stop?
When we could do it recursively, and then we'd stop when we get back to the top layer. I don't know if that would work, how I'm thinking it would work. I haven't really fleshed out how it would do it, but
okay,
it's
the way that I'm imagining it, maybe this would work. Variation. And okay, the way that I'm picturing this works is, oh, wait. No, how would this work?
Try scribbling something out, see how it would work. I was thinking it could return a vector of 2 variables because, like the teacher was saying, we only need to keep track of the last 2. So that would make things a little easier, maybe.
Going reverse. The only thing I see with the problem I see with going in reverse, and I don't know how to solve this solution, is if we're going up, so n plus 1, n plus 2, and we're starting at n, how do we know we've hit our number that we're going towards? Because we're just going to be going to, we're not going until we eventually hit a 1 or a 0. We're going until we hit whatever.
Yeah, that's a good point. We could just give it a second variable to tell it where we're going up to. And if it's, so we pass 2 variables to fib and recurse var, and one of them is the value we want to calculate in the sequence, and one is tells us when to exit. So if we're calculating the one that we want to exit at, then it stops. So we pass another variable to tell it where to exit, and if it's equal.
That's a great idea.
Yeah, I don't know if I explained it well, but
I understand it. I'm
yeah.
trying to conceptualize what it in itself is doing. Okay, so if start is if finish is less than or equal to start, return, what are we returning?
I think a vector too wide or an array too wide, because we need to keep track of 2. At least that's what I think we'd have to do.
Excuse me, can you share code so I can edit it?
I think it is. Oh.
No, I don't see it. It's
yeah, I can share it. Yeah. And then and so Oh, I need to go over here, chat. Like that.
Oh, you didn't quite share the right link. It doesn't grant access, so go share again. Invite with the friends with the join link.
I guess. Okay, I'll just try a new one. Click that twice. Just in
No,
case.
don't copy the repo link. Copy the join link. That's how you.
Gotcha, gotcha.
That's how you get access to
Yeah.
edit.
Now, if I could open chat, that would be great.
How's it going, guys?
How's it going?
Fine.
Slowly.
Trying to open chat so I can.
We're just trying to work on simple.
We had an interesting question.
We're trying to do Fibonacci going upwards.
Yeah, sure. Do you want to do it now, or
We
No,
didn't
no,
figure
no.
out how to do it, so
you know how to do it?
This
no,
would
we
be
do not
plus
know how to
one.
do it.
Okay,
We haven't figured
yeah,
out
sure.
how
Obviously,
I
this
this
can,
would
I
be
can
works.
show
plus
you how to
two.
do it. So when you
Right.
want to do it, so I mean,
Now we start.
what do you mean when you want to? What do you mean when you say you want to go upwards? You want to go from 1 to n instead of n to 1? Is that what you mean?
Yeah, precisely.
Yeah, okay, all right. So if you want to go from 1 to n, the recursive solution is going to be really, I don't even know if it's going to be possible, because so from n to 1, you can imagine a tree like this, but from 1 to n, the tree needs to. So I don't know how. I'm not able to visualize the.
But I thought of something better that we could
Right.
probably do.
However, let me show you a two-liner where you can do exactly what you want far more efficiently also, right? So is this yeah, Fiban, right? So Fiban, yeah. So can you comment out the code and yeah, comment out the code and let's start again from the
Yeah.
you can comment out the existing code. That's fine. Yeah, just the if and the return can be commented out, and let's start a new code block where the if used to be, right? So yeah, and don't just pass n, don't pass start and finish. You just pass n, size t n. Now all we want to do essentially is start from 1 as the first term and go forward. Yes. Okay, all right, so here's what we'll do. So for let me see. All right, let's say yeah, let's do it this way, and then we're going to condense it. Okay, so array, declare an array of n integers, right? N size t, right? Size t, fibs. Just say fibs, size t fibs. No, it's an array inside of the function. Declare an array called size t fibs. Yeah, and then of size n. Size I think it's got to be size t space fibs and then
size t space fibs. Yeah. That's right. Sorry, that's a Java way.
Yeah, exactly. It's fibs a square bracket n. You got to give it the size n, right? And then close. All right. So now we have this is a native array, not even a vector. Okay. So it's very lean and thin. Okay. It's just a block of memory. So it's n times size t is 4 bytes, right? So for 4n bytes of memory, bam, like that, given to you. And that memory is on the stack, right? We'll come back to this later, right? What memory is on the stack, what memory is on the heap, right? So this memory, so that is indented in. Okay. All right. Now let's say fibs of 0 equals 0, fibs of 1 equals above.
Oh, my bad. Yeah.
Fibs of 0 equals 0. Fibs of 1 equals 1, right? Fibs of 0 equals 0, right? And then fibs of 1 equals 1.
That's smart. I didn't think of this.
Yeah. All right. Now enter. Now you can do a for loop for n equals 2. No, for int j equals 2 to n. You can do a for int j or k or whatever. Yeah.
I think it's better to use size t for loops, right?
Yeah.
Oh,
okay.
yeah.
Size t.
Because then you get a warning.
Yeah. So size tj.
It doesn't matter, but
j less than or equal to n. J less than or equal to n.
J plus
plus, and I think where you declare the array, make that n plus 1. So we want to go from 0 to n, so the size of the array has to be n plus 1 elements.
Gotcha.
Yeah. All right. Okay. All right. No, you don't even need braces. This is one line, right? So it's just one line. On the next line, you say fibs of j equals fibs of j minus 1 plus fibs of j minus 2. All right. So you can get rid of the braces. That's it. And then you return fibs of n at the end.
Okay.
So this way you go from the first element to the last element, and you never ever compute the same element more than once. Yeah, yeah, really
Yeah.
cool. Yeah, you can get rid of the braces. It's all one line, and you just return fibs of n at the end.
Yep.
Now, here's the cool thing, right? So in fact, you'll find if you look at this code long enough, you'll find you don't actually need an entire array. You only need two variables, right? You just need two variables, and you can just reset these variables in a loop, and you're good, right? So that I can leave as homework. You can find out, right? It'll probably take about a half hour of thinking, all right? Half hour or less of thinking, where you find that you don't actually need an entire array. You just need two extra variables on the stack, right? Right now you're getting n elements on the stack, right? So this is n, so you don't need n. You only need two. This is really, really thin, fast function, right? And it's linear, and no matter how big n is, bam, you get the answer immediately.
Mm-hmm.
Does that make sense? That is how you do it, forward, from, I think, starting from one, going to the end. If you want to do it recursively, I think it's harder. Try and figure it out. I don't know if there's an easy and straightforward way. You have to have messy things like, accumulating parameters, and you still have to keep count, because it's, the problem really with the recursion here is that it's doubly recursive, right? It's singly recursive, it's different, right? Singly recursive factorial you can do either way, right? If it's doubly recursive, you have two descendants calling the same parent. Yeah.
Mm-hmm.
So that gets messy to implement, because then you have to distinguish these calls by parameters that you pass. And recursion will get messy, that way. And then, who knows, in the end, you may end up implementing a stack and doing all the crazy things the system is going to do for you anyway, right? So that's usually what I end up, I find happens, is that when many times we have an elegant construct, which sometimes a little, we try to optimize, and we do some crazy things. And we keep on doing crazy things, right? So many different crazy things, and then eventually we end up at what the system gave us anyway, because they've, very, very intelligent people have tried that for several tens of years. Right, and they've decided, okay, well, we've tried all these different ways of running things, and this is the one that works best of all, right? And then we said, to hell with all these intelligent people, I know better, I'm going to do this, right? And we do that for 2 years, and we say, no, actually we should do this, to modify that this way. And then by the time we've forgotten how we got there, right? And I modified like 10 times, you've forgotten where you came from, and then all of a sudden you come back all around in a circle and hit the first time what you started with, and say, that's really the best of all worlds. Right, and that's what the designers have been telling you from day one onwards, and so that's kind of cool. All right, so is that okay? Is that enough homework for you guys? We can start talking about stacks if you want.
What's the homework?
Yeah, I think I mentioned the homework.
I think I do remember.
The homework is try and make it so that you don't have an array. You only have two variables, right? So this is the iterative dynamic programming version.
Actually, I worked on this at home myself, so can I show it to you?
No, just share it on the forum, not here.
That's what I meant. I mean, show it on the forum.
Oh yeah, totally.
The only problem is it might be a Quest thing. That's the problem.
No, if it's a Quest thing, don't do that, right? So if it's a Quest thing, oh, I see, it is.
Because the Quest does have you do this similar method that we're doing right now.
Okay, all right, let's forget it then. Let's not share it, okay?
Because
I think if it's in the Quest, I think I must have decided that it's.
I actually did it with two different variables, and we
No, that's fine. Yeah, I understand how you would have done it, but I think if I put it in the Quest, I must have at some point discovered that it's too juicy to be disclosed, right? So it's something that it would be more fulfilling if you find yourself. So don't post your solution.
I use like M1 and N2, but I'm not going to explain how it works.
I'm sure.
And it's
great. I'm happy that you got it to work, but don't tell any more about that. Don't talk about that. Okay, let's figure it out.
Yeah, I got it. And I just had a temporary variable to swap it.
Yeah. Fine. That's great. All right. Thank you. Thank you very much, Chad.
So technically you do need a temporary variable if you want to swap
I don't know. Different people may choose to do it different ways. Okay, let's not belabor this anymore. So people are free to do it however they want. Try and come up with the leanest, slimmest, nicest implementation you can, and share it if you want. Okay, so that'll be cool. But don't give away. If you think you've come up with a solution that is required for the Quest, don't worry. You have other opportunities to post other things in the forums.
So how about a better question? So I've been trying to understand a stack not the Java one, but I mean, the one that for compiling a program. I'm looking on the website, Microsoft's website, to find out. So is there a good summary? Find it.
Yeah, I mean, you can just find it on Wikipedia, anywhere. Stacks, there's such an old data structure. You can find it anywhere. Linked lists.
Will thread stack work? Is that what they're called?
Just say C++ stacks. Yeah, but forget about that, Chad. All right, let's talk about it. You can do all this in your spare time. All right, all you guys.
I'll just do that during my spare time. I'll learn about what stack is.
Do it in your spare time, whenever. All right. So, so here's what happens. Okay. So, do you guys want me to talk? What time is it now?
It's 9:40.
9:40. Okay, so we got about 15 minutes. If you want, I can talk about. If you're interested, I can talk about what happens when a function is called, where the system stack comes.
Yeah, I'm interested. I wonder why.
Oh, well, I know you guys are interested. Okay, I want to hear from more people. Okay, not just the 5 of you. All right. So, yeah. Can people say that if they are interested to know what would happen if when a function is called, where the stacks are, and how the stacks come into play? Yes, type in yes or no.
I'm interested.
Yeah.
Okay. All right. All right. We'll talk about that. 15 minutes. Give me a buzz or something, or let me know if it takes too much time. All right. So every time, so when you've written your program and your compiler has had a chance to look at it and kind of translate it into machine code, and now it's all ones and zeros, and it's all stored on hard disk. Okay. So on your hard disk, right? Not in memory. Okay. Remember, not in memory. On your hard disk, on your magnetic media or solid state device on your phone, whatever it is, right? So on your disk, in permanent storage, in ice cold storage, in the freezer, your program, which has been translated into CPU instructions. All right. At that point, it is all CPU instructions. Yeah. So, you guys have got to chime in. Anytime I say anything that doesn't make sense, you got to say, all right, hey, stop there. All right. Can you say something? All right. Raise your hand.
I understand. Yeah, that's what happens when compile.
Your program is translated into CPU instructions, ones and zeros. I always say, saying this is exactly what you need to do, dear CPU, right? And those bytes, which stand for your instructions, they're actually stored, right? Maybe your program got translated into 15,000 bytes, right? 15,000 bytes of information, 15,000 bytes of instructions, right? So they got stored in a file that is 15,000 bytes. I'll probably show you a demo. I don't want to log in and and open up a terminal, but you guys are welcome to, right? So I think you do ls-l on the terminal or in the shell. You'll actually see all these files and sizes of files, right? Yeah, click on the shell prompt. You can try various things as I'm typing, right? So in the terminal on the right side, in the dark section, click on the shell tab in the terminal, and the replete, you'll see it, right? So anyway, as I was saying, so it's in memory. So anytime, what happens is that the boot up process of the computer, when the computer boots up, a program is run by the system automatically. It is called a shell. Okay, the shell is a program that sits between the core services provided by the operating system, because the operating system provides a whole bunch of core services to anyone who comes asking. The operating system is what controls the CPU. This is like a mini course in computer architecture. Are you guys interested? Right. Okay. So the operating system is the CPU is the workhorse. Okay. It's right in the middle. It's in the center of the universe, right there. It's in there. The operating system is a kernel that covers the CPU. Right. So people can't access the CPU directly. When you go poking into the needles, they can't do that. The operating system sits on top of that. It's actually a software layer, right? It's this program that sits on top of the CPU saying the CPU can do lots of things. I'm not going to let you handle all of that. However, I can give you the power of the CPU. I'm the gatekeeper for the CPU. All you need to do is tell me. Excuse me. All right. So the operating system says, I'll give you a bunch of facilities, right? Facilities. They calls it system calls, operating system calls, right? So the operating system provides a bunch of handles to the external world, saying, okay, I'll give you a handle to jiggle, right? I'll give you a bell or a door to knock when you want a file to be open, right? I'll give you another door to knock. Or a counter, right? Another counter to go to when you want to, let's say, add two numbers, right? So when you say I got a number there, I got a number there. No, I'm talking about operating system, not CPU, right? So the operating system has higher levels. This is to talk to the screen, right? If you want to talk to the screen, right? Here's a window you need to go to. Take the screen, send it to the window. That window will send it to the screen. Here's another window, right? It has the latest thing from the keyboard, right? Here's another one. So it gives you like a million windows. It gives you a million, and each one of those is called a system call, right? Because that is done by the CPU, but you can do it directly. You tell the operating system, and the operating system will get the CPU to do it for you. So far, everybody on the same page? Is that okay?
Yeah.
All right, so those are the operating system achieve. So obviously, the calls provided by the operating system, they are not like and not anybody can just go marching in. And they're like C++ library calls. They're called library calls. This is system calls. They're built into the operating system so that they're right there in a dynamically loaded library, and they're C++ functions. They are C++ functions that are right there in live. They're in a daemon, right? They're C++ functions waiting to be called. They're right there. Right? If you can look into the operating system, you see, oh, there's a function called open. Open is actually a function. It's a system call. And the operating system provides a system call called open, and open takes parameters, just like a regular function. C++, these C++ functions, right? So the open system called an operating system says, give me the name of a file, give me all these metadata details whether you want to open it for writing or truncating or reading, right? So give me all those details. I'll get the CPU to do that, and I'll return to you just a number. Right? Look at the beauty of this, right? No matter what you're writing to, whether you're writing to a satellite in Mars, right? Whether you're writing to rover, right? Curiosity or something like that in Mars right now, whether you're writing to a file on your disk, whether you're modifying a Google Doc document, doesn't matter, right? Whatever it is, the operating system says, you don't have to worry, okay? You don't have to worry. All you need to do is tell me you want to open that, right? And you tell me when you want to open that, I'll give you a number. Okay, I'll give you a number. It's actually a number. It's an integer. You can look at it, right? It's called a file descriptor, right? And you don't know what's behind the file descriptor, right? Behind the file descriptor could be a whole universe. It could be a whole universe, basically a point in Mars, but basically intercepts the signal and transmits it to Andromeda or something like that, right? So you don't know, but all you know is that you have an integer into which you can send stuff. So you got that wormhole into that universe. So the operating system will give it to you if you ask. Right, so and that's the beauty of many of these operating systems, is that they hide all the complexity from you. Just like C++, all the complexity is hidden away so that you only have to deal with these integers. Right, so there's these, so that is the because they're all C++ calls. Ordinary programmers, on the shell, I'm interacting with a computer. How can I interact with the computer if I can only do C++ calls? Obviously, when I type in commands in that computer, ls-l and hit return, right? It's the operating. How does the CPU actually see it? What happens is that as soon as the operating system comes up and makes sure all the library functions are loaded and ready to go, it'll fire up another program called the shell. It is a special program, right? It's called the shell. The terminal is called a TTY interacting program. It is another program. You own that program. That program is being run as you, right? As though you fired up the program, it is automatically run. It's like this automatic running program. Every time you log in, it'll be run for you automatically, right? And that program has only one job to do. And that program will listen to you and listen to the operating system and then communicate back and forth. That's all it does. That is called the shell, right? So you got the CPU and you got the operating system, and then that's the kernel, right? It's the kernel, and you got the shell out of it, right? And then all the users out there, the users talk to the shell, and then the shell will say, okay, this is what the user wants to do. I'm going to translate that into stuff that the operating system can understand and send it to the operating system, right? And then the operating system takes what the shell told it and say, oh, this is what the shell wants me to do. I'm going to translate that into stuff that the CPU can understand and send it to the CPU. The CPU will do that and return the result to the operating system. Operating system says, okay, I'll send it back to the shell. The shell says, okay, that's done. I'll send it back to the user. And the user says, oh, I got it on the screen. So let's do that really quickly here, okay? So on this terminal, type in echo hello and hit enter. Echo space hello.
Yeah. Sorry, I was taking notes.
Yeah, it's fine. It's all recorded. You don't have to take notes. Yeah, it's fine.
I keep forgetting that.
Yeah, I know. Everybody.
I'll go back and look at the recordings actually, because there are a lot of things I miss. Just a lot of information in front of me, so it's easier to process.
Sure. No worries.
But I always still take notes during the lecture, because I'm always like, oh, this is like I'm used to lectures where it's like, oh, this is the only time I'm going to hear this, so I better take some. Anyways,
even before in my class, recording is a boon really for us. Yeah, and no, not there. In the black terminal, type in echo hello.
Oh, echo, what is it? Oh, wait, hold up, let me mute my, yeah.
So I have a question.
Echo.
Yeah, I hear Susanna, your voice is very, very low. Maybe my microphone. Echo space, and then something, you know, punching a bunch of keys and hit enter. Yeah, enter. Okay, there you go.
Okay,
so
cool.
It basically echoed stuff back to you, right? Now echo, if you do, what is echo, right? So do ls-l, ls space dash l, ls
space
dash
dash
l, dash l, dash little l,
like that?
space, 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 slash bin, slash bin.
Oh, I know, okay.
Echo, slash echo. I hope that's where it lives. I don't know. Echo, no, ACHO, no. Oh, it's there,
So-
it's there. Right. So see, there is a file. That is a file. Okay. So this is basically Unix for those who, even in DOS or a Mac or anything else, right? You can do this in most of the time it'll work. Except in DOS, maybe it's not ls-echo. Right. So so bin echo. So echo is a program. Someone wrote a program called echo.cpp. All right, just like you guys are writing hello.cpp, someone a long time ago in AT&T Bell Labs wrote a program called echo.cpp. All right, and we can write the program. It'll only take 5 minutes to write it if you want, right? So all that program does is basically, and we actually wrote it. There's a recording of that in our non-linear media channel, right? There's actually a recording, a 5-minute recording of someone actually writing an echo program. Okay, and so echo is basically going to take whatever the user says and it's going to echo it back to the user. Now you may look at it and think, well, nothing much really happened here, but you know, a whole lot of shit happened there, and we just don't see it all, right? But what happened was that the shell said, okay, the first thing I need to do is that there is this program called echo that needs to run. Where is that program, right? So now, because you didn't say that the program lived in a directory, in a folder called /bin, right? So /bin is a home, some address, some on disk, right? Somewhere, echo, there's a program called echo, which consists of, I don't know, 35,000. What was that exactly? 35,000 bytes. Well, that's fine, right? So there's an echo program that has 35,000 bytes of instructions, right? And it lives in a folder called /bin. But when you invoked echo, you didn't type in /bin /echo, you just said echo, right? And a shell went and found echo in that directory. How did it know that? Because it has this variable. Your shell has a variable called path. Okay, so echo. So type echo, echo, space $path in uppercase, $path uppercase.
It's funny. I've seen like,
no, uppercase.
Oh, my bad. Dollar path.
No, all uppercase, all uppercase. Yeah, that is title case. You know, what you did is called title case, I think. Uppercase is all letters. Uppercase.
Oh, all caps. Got it. Path, like that.
Yeah.
Got it.
Okay, so there you go. So so that variable, which you can change, by the way, if you're into all these things, right? So basically says when someone types in a command that you don't know where it is, these are the directories where you have to look if those commands exist. That command exists in those directories. That's what it means. Path means the path of all the directories where you got to search. Where the path is where you search for the command that has been asked for. So echo lives in one of those directories. I'm sure /bin is somewhere in there, in that list, right? So it found it there. So what the shell did at that point was, okay, the user wants to run the command echo. Let me go and find the command echo. Oh, it lives in the path in /bin. Okay, so let me go and ask the file system, right? So many things happening, and you'll be surprised, right? So at that point, the shell says to the operating system, fetch the contents, right? Even before that, it does a bunch of system calls to find out where it is, right? But we're skipping all that. It says fetch the contents of a file which lives in that folder, and it's called echo. And these are the details. Go and get me the contents, right? And the operating system, this is the shell, right? So, and here's the user who said echo, right? And the shell says echo, right? And then the operating system get me the contents of the file echo, right? So the operating system says, oh, here's the 35,000 bytes that were stored in the disk, right? Because the shell can't access the file directly. It has to ask the operating system. The operating system goes, gets the 35,000 bytes, gives the shell, and then the shell says, okay, well, now I've got 35,000 bytes. What I need you to do is also take those 35,000 bytes and set it up as though it is a program supposed to be executed very soon. Does that make sense, right? Because you can get the file contents, but you can get the file content for many things, right? You can get it for reading, you can get it for writing, but in this case, you're getting it for execution, right? So the shell says, take that file, the contents of the file, and lay it out in memory, in real memory, not on disk anymore, not on cold memory, laid out in hot memory out there, and remember where it is, right? Because not there yet. Remember, okay? So it takes a program, puts it out there in memory. 35,000 bytes fit into main memory in RAM, right somewhere, fits there, and it's there. And then the operating system says, well, there's other stuff that needs to be given to this echo command to run. So it takes these arguments and says, well, these also need to be passed to the to the program that's going to be run very soon. Not yet run, it's just been loaded. It's loaded, right? So take these strings, right, which the program, when it becomes alive, it's going to start asking for these strings. So take these strings, these other strings that the user has given, and put them in an array somewhere else in memory. So it puts them in memory too, right? Tells the operating system, puts them in memory, right? And then it says to the operating system, now fire up that program. Right, now fire up the program. And the operating system now tells the CPU, right, so I have a bunch of instructions for you starting at memory location XYZ, right? Go and start executing them. So far, are we in step? Because it's a very, very intricate dance. It's
interesting. I think this is very interesting. I wonder is that why calling gives overhead? Is that why, calling stuff gives overhead?
No, we haven't gotten to the place where we get to the calling and overhead.
But, it's interesting. The shell calls the OS stuff, right? It's interesting that the shell actually is what tells the OS.
The shell mediates access to the operating system. You can't talk to the operating system directly unless you write a C++ program.
Cool.
Right?
Yeah. I mean, C++ that usually talks through the shell, really, right?
No, C++ can talk directly to the operating system. Right? You can in your C++ program, you have the ability to talk directly to the operating system by issuing system calls.
But usually you talk to you.
That's only if you're not writing C++. If you're interacting through shell, like Peter is doing now, then you're
terminal, right?
No, that is a shell. Peter is interacting with the shell.
Cool.
The kernel has.
Got it. I mean, it's like PowerShell, right? PowerShells.
Yeah, all these shells are these shells. The shells, and the kernel supports all the low-level operating system calls. Like compile and so on. So
yeah, but this is interesting. Oh
yeah.
Remember, look at the time. Remember the time. You see.
What time is it?
9:56.
Okay.
So either I could just do it in my own free time, or you could just explain.
Yeah. So here's the options, guys. Well, let's see. A bunch of people have dropped off. There's still a number of people here. I don't want to carry on this conversation for that the others might have followed. If someone can on Tuesday. Well, here's two options, right? Either we pick up here on Tuesday, and then I can talk more about how the program gets loaded and where the stack comes in. We haven't really started talking about stacks yet, right? So where the stack comes in and all these things, we can do that on Tuesday. Or if you guys like, pick a time between now and Tuesday. And pick a time. Thursday, I got a meeting this afternoon. Yeah, I'm relatively free tomorrow. Or weekend, I don't care, right? So we'll coordinate a time. I'm mostly free. So pick a time. I'm happy to talk about these things. Right, at least 2 or 3 people, right? Not just for one person, right? I'm happy to do that, or we can do this on Tuesday, right? Not a big deal. There's a lot of interesting things here, and incredible stuff that goes on, right? So you just saw one command. There's so much happening in the background in order for you to get that result, and it is magical. Just looking at everything, all these people have to dance. All these people have to dance are very strictly choreographed and a very synchronized dance, or you're not going to see the results, right? And then we just take for granted. I mean, you type it in and it works, right? But no, it's so much has to happen in order for that to work, and and it is really useful to appreciate that. Yeah, all right, thank you guys. Anyway, I think
I think one of the coolest things about as I learned how code works, like something like this, like learning this part is and I'll start sharing though. Stop sharing. But it's interesting because I slowly but surely learn more and more of like how when my computer has a problem and it throws a bunch of 100 different lines of debugging code at me, and I'm like, what am I looking at? I can actually piece together slowly but surely. Like when I look at it, 2 years ago, I would be like, yeah, that's a bunch of gibberish. I'm not even going to care about that. And a year ago, I was like, oh, I can read a little bit of this, but most of it doesn't make sense. And now I'd probably look at it and go, oh, I could understand 7% of it. I can understand enough to see what answer it got, definitely. I don't really know a lot of what it did, but I can understand the general concepts. And I think that's cool. It's slowly but surely seeing when something small happens, like a program fails and it gives me a big error or something like that. I actually know generally like what it's talking about. Which is I think is cool. Like as there's all these things that just seemed like just alien words to me about my computer, especially that have slowly been deciphered as I learn more and more about
and
code.
it's better. Yeah, it gets and
So
yeah, and
I'll see you later.
Yeah,
I'll see you later.
Right.
Is that fine? I
Bye,
go
Jen.
now
Yeah.
because it's time. Remember.
yeah, absolutely.
Right. See you, Jen.
Thank you.
Okay.
Thank you.
I'm
guys.
going to have breakfast right now.
All right. All right. So let me know if you guys want a class, or we'll meet on Tuesday.
I'd love a class, yeah.
Yeah. All right. So
I would
coordinate
mind.
something. Coordinate
I'm fine.
something, and yeah.
So
And we'll make sure that we don't cover anything that is required material for 2A, so that people who don't attend the optional class miss out, right? So
and I have
there's a lot of stuff
I
we
have
can
some,
cover. That's not CS2A.
the optional class is when next week or when?
I don't know. You guys can find a time and coordinate, right? I'm relatively free most of the time.
A question, just a quick question.
Mhm.
So is it maybe I can just find why CPU calling does overhead on my own free time, right? I'm just going to do that.
Sure.
Yeah.
Absolutely.
I'll just do that because you didn't quite go into that. You were going to shell, but you ran
No,
out
but
of
we'll
time.
go into that on during the next class for sure. I think.
Cool. But I'm also going to look that up. You know, that's.
That'd be interesting. You can find what you can
Maybe
find.
can I
whatever you
actually
find
explain
and
it
then-
to you?
Uh,
If you want.
on
Hey,
Reddit.
hey, Chad. So can I take can I take off? Is that okay? You guys can.
Yeah,
Yes.
I'm talking about like next class.
Oh, next class. That's fine. That's
See
fine.
guys.
Okay.
Next class,
all right.
can I explain, or maybe on Reddit, on why
Yeah,
calling
Reddit
takes
is better.
overhead on like
Reddit's better.
macros?
Yeah,
just
do
explain
Reddit.
it, yeah, in Reddit. Just explain it in Reddit, and then we can explore it next class.
Cool. Bye.
All right. Thank you so much, guys. I'll see you next time. Okay.
Yes.
All right.
Thank you.
Bye.
Bye.